Oh, hello, friends. I didn't see you there. I was deep in meditation in the forest. If you notice, I finally got that yellow lightsaber I was telling you all that I wanted. I just had to find the right kyber crystal. But this is an example of one of those times where your science teacher shows you something and they're expecting you to have some grand revelation upon seeing it. Um, if you look, this lightsaber is not doing what we're studying. That is to say, this isn't rotating. Even though it is precariously perched on one finger, it's not rotating. And in fact, because my finger is in this one very particular spot, what we call the center of mass, or what some people will instead call the center of gravity, or if you are uh, really well versed, you might call it the barycenter. But because my finger is under that point, whatever you call it, this does not rotate due to its weight. It's like a free body diagram. The lightsaber has all of its weight. Mg is coming straight down from here. The support force from my finger is going straight up to the same spot. And so much so that it sets off alarms. And it cancels out. Net force is zero. And if I apply a force here, the whole thing lifts without rotating. But if I apply a force anywhere else, for example, this, it does rotate. Thus, this point must be very important for us in our studies of rotational motion.
So center of mass is an imaginary point in an object or a system made of several objects where you can assume that all of the mass is located. Even if it's not quite true, it works enough for an approximation of it. The other definition of center of mass, and this is probably more along the lines of what you were thinking of it, it's definitely the easiest way to visually identify where the center of mass is. It is the point where all torques on an object balance out. Now, what is a torque? You've probably heard this before. It's mentioned often in commercials for trucks. It is measured in imperial in foot-pounds. So you have a distance measurement and you have a force measurement. Well, a torque is a force that causes an object to begin rotating, stop rotating, or change the speed with which it rotates. In other words, a torque causes angular acceleration, be it you get an increase in angular velocity or a decrease in angular velocity. So it is the rotational equivalent of force, whereas force is mass times acceleration, torque shall be moment of inertia times angular acceleration. So a torque causes angular acceleration the same way a force causes linear acceleration. But we'll revisit torque in a moment. For a uniform object, it is usually safe to assume that the center of mass is located in the center of the object. Why? Because it's uniform distribution. Imagine a meter stick. Meter sticks are usually pretty uniform. They don't vary too much in density as you go up or down. You don't have them vary too much in width, so there's not like one part that's bigger and more concentrated or anything. So they're a good reference point for uniform beam. Uniform beam being the most common term in torque problems because it makes it very obvious where the center is. But if we treat a meter stick as a uniform beam, then does this first centimeter right here of our meter stick have weight? Sure, it's got a little bit of weight. It's got mass, doesn't it? But the problem is, on the other side, there is the 100th centimeter that has weight as well. These two both bring it down. If you had your finger right here and you cut this one off, this one would be unbalanced, the thing would rotate. Similarly, this one is being canceled out by that one. Same thing for the next few centimeters, next few centimeters. These two are canceling each other out on each side until you get to the middle. If you put your finger in the middle of the meter stick, you have found the center of mass. You support that. You support the effective weight of the whole thing. Now, what is it that you're really doing? There's as much weight on one side of your finger trying to get it to rotate this direction as there is on the other side of your finger trying to make it rotate in this direction. So you're supporting all of the mass, and you don't have to worry about the mass on either side accelerating. To find the center of mass is very easy on uniform objects. Like I said, they have their center of mass in their center. Uniform distribution of mass will do that. If you have something that is not uniform, for example, the lightsaber. When I have the lightsaber balancing, you see that the center of mass is way more so on the side of the hilt versus the blade. Why? Because the hilt is made of metal and it's heavy and it contains batteries and all the electronics, and the blade is hollow and made of polycarbonate. It's lighter. So the mass, most of it of the lightsaber is on this end. So the center of mass is usually located closer to the larger object if you have a system of objects, or the heavier end of a non-uniform object. Imagine we have a system of a 4-kilogram object and a 1-kilogram object. Where would the center of mass between these two be? That is, if we placed them on a massless beam, or if they were next to each other in space in some sort of orbit, blah, blah, blah. If we wanted to figure out where the mass of these two is, how would we do that? Well, for non-uniform objects to find their center of mass, the location of the center of mass, typically given as an R. Keep it straight, we can do center of mass as a subscript so that you know what you're looking for. But the center of mass can be found by taking the sum of the masses times their separations from some reference point, and dividing by the sum of the masses in the system. Again, N is the mass of one of the objects or the entire object, whatever, in kilos. And R is the separation from reference point in meters. If these two weights have their centers separated by 2 meters, then that is absolutely enough information to plug in and find the center of mass of the system. All we have to do is decide on a reference point for these to be separated from. And what is typically done is you put it wherever you would make your math easiest. I think I will put my reference point in the center of the 1 kilo object. And the rest is going to be a cakewalk. So we need the mass of that, which is 1 kilogram, times its separation from the reference point. Well, the reference point, which I marked with a little triangle representing a fulcrum, again, terms we'll get into in a moment. Well, it's not separated from it at all. Its center is the reference point. So it has 0 meters of separation. Sum means add 4 kilograms of the other object, and its center is 2 meters away from the reference point, in the middle of that one. The sum of masses would be 4 plus 1, 5 kilos. 0 times 1 is 0 kilogram meters, plus 4 times 2 is 8 kilogram meters. 8 kilogram meters plus 0 gives you 8 kilogram meters, divided by 5 kilograms. Cancel out units that are common to the numerator and denominator. And the location of the center of mass of the system is 8/5 of a meter away from our reference point. That would be 1.6 meters away from our reference point. So if this whole thing is 2 meters long, then at the 160 centimeter mark from here, we have the center of mass. If these two were in an orbit, they'd both be circling that point. If these two were on a seesaw with a massless beam so that it doesn't throw off our balance, we would need to put the fulcrum right here to balance them out. When you have multiple objects in a system, you can also call the system's center of mass the barycenter, especially if they're orbiting each other. For a favorite example of that, of mine, of course you guys know that I have my physics roots in astronomy. Here we have Pluto and its largest moon, Charon. Of course, there's 4 other moons, one of which has a leopard gecko named after it. But Charon is the largest moon, named after the ferryman of the dead, who takes you across the river, Styx, or whatever to join the underworld. Should be pronounced Charon, but the guy who discovered it wanted to name it after his wife. The IAU says you can't name it after your wife, you have to name it after something from mythology, preferably something related to Pluto. So he looks it up in mythology. Are there any characters related to Pluto who have a name similar to my wife? His wife's name was Charlene. And turns out there was Charon, Charon. He decides, well, if you pronounce it like Sharon, that's kind of like Charlene, Char at the beginning of both. So most American English speakers will pronounce it Sharon because you're paying respect to the guy who discovered it. Other countries, they don't have to respect American astronomers, which is a damn shame considering Pluto itself was discovered by an American astronomer, Clyde Tombaugh, in 1930. I digress. I'm supposed to be talking about center of mass. Well, Pluto and Charon do this really interesting thing as they orbit. Here is a series of real pictures taken by the New Horizons probe, not Animal Crossing New Horizons, the New Horizons probe. It was a space probe that we sent out to Pluto. It went past it in 2015. And here you see that X marks the barycenter of the Pluto-Charon system. and both of them are going around it. It's not like the sun and earth, where the sun weighs so much more than the earth that the barycenter is deep within the sun and very close to its center. The sun appears to barely wobble while we make this huge arc around it. Or even the earth and moon, which is similar. It's a little bit further out from the center of the earth, so we wobble a bit more heavily. But Pluto is straight up orbiting a point where there's nothing. The barycenter, they're both turning around it, and it's not located in either of the objects. Really interesting stuff. If you wanted to make a case for Pluto being a planet, say, hey, look, just add Charon's mass to it and count it as a binary planet. Of course, if you adopt that definition, we also have a really, really large moon relative to our size. So Earth would be another good candidate to be considered a binary planet. But let's use this as a setup for a center of mass problem. Take some of the measurements from Wikipedia, and we can get to work. All right. So the separation between Pluto, the symbol for Pluto is a P with a L's leg. Not only is it the first two letters of Pluto, it's also the initials of Percival Lowell, because in 1930, Clyde Tombaugh discovered Pluto at the Percival Lowell Observatory on Mars Hill in Arizona. So the separation from Pluto to Charon doesn't have a symbol because it's just a moon, is 19,771 kilometers. The mass of Charon is 1.52 times 10 to the 21st power kilograms. Is considerably lighter than, say, our moon, because our moon is made of rock. This thing's just made mostly of ice. And Pluto is 1.31 times 10 to the 22nd kilograms. Not that much more than its own moon, hence why the center of mass is located somewhere between them as opposed to being inside of Pluto. Let's figure out where they balance out. We need to decide which one of these is going to have our center in it. Typically, the larger of the two objects is considered the primary in the gravitational system. So since Pluto is the dwarf planet, it's the primary. Let's call the center of Pluto our reference point, which means that to find our center of mass, Pluto is not separated from its own center of mass. So it's going to provide 0 kilogram meters to our process. Charon's mass, 1.52 times 10 to the 21 kilograms, is 19,771 kilometers away. Divide by the total mass of the system, 1.52 times 10 to the 21 kilograms plus 1.31 times 10 to the 22 kilograms. And we will figure out how far out from Pluto's center the barycenter is. 1.52 times 10 to the 21st times 19,771 kilograms divided by 1.52 times 10 to the 21st plus 1.31 times 10 to the 22nd. And we get 2,050 55.5 kilometers away from the center of Pluto. Well, Pluto, from here to here, that is from the center to the surface, the radius of Pluto is 1,195 kilometers. So we can take our answer, and this should be 860.5 kilometers outside of Pluto. And we've found the barycenter of the system. This center is what goes around the sun. So similar to how when I had the lightsaber balancing on my finger, I could just apply a force to that point, and everything in the lightsaber went in the same direction at the same time. The sun pulls on that point, and that point goes around the sun, dragging Pluto and Charon along with it. As above, so below. Another really common and much more down to earth, much more down to earth, not a space anymore, type of center of mass problem will be the seesaw. Do they call them seesaws down here, or is it teeter-totters? Is that a Yankee thing? I don't know. Imagine we have a child on one end of a seesaw, and on the other end of a seesaw, we have a grown-ass man. All right, so there's our setup. The question is, where do we put the fulcrum so that the child and the grown-ass man reach equilibrium? And that is to say, they balance out. Well, we would need the mass of the child, let's say 50 kilograms, and the mass of the man, let's say 200 kilograms. And the last thing that we would need is just like in the previous problem where we needed the separation between Pluto and Charon's centers of mass, we would need the length of the board. The length of the seesaw, I don't know. Let's call it L. All right, L equals L. We're really doing some high test stuff here. And what we want is the location of the center of mass. Well, we need to decide what our reference point's going to be. I don't care whether you make it the child or the grown-ass man. Let's say the child is our reference point. So the location of the center of mass is the middle of the child, or the center of mass of the child. Should be 50 kilograms times 0 meters, or how much it is separated from the center of mass of the system. For the grown-ass man, 200 kilograms, an entire length of the board away from the kid. The sum of masses is 250 kilograms. All right, almost there. We can get rid of stuff that's on the top and the bottom. So we have 20/25ths, or as I like to call it, 4/5 L. So it doesn't necessarily matter what the length of the seesaw is. It could be 20 meters, it could be a meter, it could be 2 meters. No matter how far the separation is, we would need to put the fulcrum 4/5 of the length of the board away from the child. That is to say, closer to the adult, which is, again, not surprising. Just like with Pluto, just like the lightsaber hilt, the heavy thing has the center of mass closer to it. There is an alternative approach that deals with the second half of this lesson's title. The alternative approach would be to treat this as a problem that involves torque. A torque is a force applied some distance away from the center of mass, because if it acts in the center of mass, you get no rotation. So it's a force acting a distance away from the center of mass that causes the system or object to rotate. Now, that is an oversimplification. That is assuming that it is not rotating at the beginning. If you want it to be general, it changes something's rotation. So if its current rotation is 0 radians per second, it'll change it to a non-zero value. If it is currently rotating and you add a torque, you might speed it up or slow it down. So a torque is a force applied some distance away from an object system's center of mass to cause angular acceleration. So if we wanted to find the center of mass for this system using torques, we would need to consider that there are two objects that are torquing the board, if we ignore, of course, the weight of the board, which we did in the last time as well. So we assume that we don't need to know the weight of the board. Where do we put it to balance them out? Then the two torques would be, there is the weight of the child, there is the weight of the adult. Somewhere in the middle, we need them to balance. A force applied some distance. That distance is called the lever arm. The distance from the center of mass at which a force is applied to cause a torque. Now this is crucial stuff. You see torque all the time. Again, like I said, it's mentioned in lots of different truck commercials. We've got the most torque. It's also mentioned on the packaging for most tools. Why? Well, think of a humble screwdriver, right? If you held a screwdriver like this to turn it, it would be much more difficult to get it to turn a screw than to hold it up here. It's not just because there is this nice grippy material. It's wider here. With more separation from the center, you get a greater torque. To find torque, remember capital T and lowercase t are already taken by time. To find torque in a linear system, or when we're worried about linear motion, we'll use a lowercase tau for torque. It is the force you apply times the length of the lever arm. Separation is usually an R. So torque is for real. And if you apply it at an angle, you kind of screw stuff up. So we have to also keep in mind that there is an angular portion to it. Now up here, our child and our adult both have their weights. If this board is balanced, it's horizontal, your weight is vertical. That's a 90-degree angle. If something's perpendicular, you get maximum torque. Sine 90 is 1. So how much of the force do you get? All of it. Sine 30 degrees would be 1/2, so only half of your force is in a direction where it can create a torque. If we had sine 0 degrees, well, think of the screwdriver. If you apply a force here, all of it is going to turn the screwdriver. If you apply a force here, it doesn't do anything to turn the screwdriver. So if you have 0 degrees, you get 0 torque. 90 degrees, maximum torque.
It was Archimedes who first formulated this famous law of the lever, and also very famously quipped that if you give me a lever long enough and a fulcrum on which to place it, I will move the earth.
A cheater bar is a common device that makes use of torque. As you can see, this wrench has been extended. The breaker bar or cheater bar is simply a pipe that you jam onto the end of a wrench. If you can't exert enough force to turn a bolt that's stuck, then perhaps you can do something else to affect the torque. You want it to rotate, so you have to have a torque. So what do? Well, you have to have a force and a lever arm. If you can't get any stronger, you can apply from farther away. So the breaker bar or cheater bar uses that to your mechanical advantage.
For an example of torque other than the classic cheater bar, every door has a hinge that acts as the fulcrum around which it rotates, and a knob typically located far away from that hinge. If you pull at that knob or handle, you've got a great amount of lever arm. More lever arm to cause the same torque lowers the amount of force required to open the door. However, if you were to try to cause the door to rotate from over here, you've got to push harder to get the same torque. Or, it's much more obvious when you open it, especially against the good suction seal of a refrigerator door. Try it with your own refrigerator. Pull from far away from the hinge, you can probably rotate it open. Try it again, pulling from near the hinge. It takes a lot more force to get the same thing to happen. Try with 2 hands. Okay. Whew. Thankfully, the engineers took the torque into account when they designed doors for the past few thousand years.
So a conceptual check. One last thing before we finally prove that you can use torque to solve the case of the seesaw. My lightsaber has a screw right here to hold in the blade. It uses a little Allen key or Allen wrench or hex wrench. These things go by a bunch of different titles. Would I get more torque, or in other words, would it rotate more easily from here with the tool set up like this? Like here, the tool set up like that. Should be obvious. This way, I've got a much longer lever arm, so I can apply the same force and get a lot more torque. If I apply it like this, I've got a shorter lever arm. I'm going to have to apply more force to get the same torque out of it. If you ever need to open a pickle jar or something that is stuck, don't hold like this, press down, and try to turn, because then you only have as much torque as the length of your hand. One time during lunch, Miss Castriata comes in with some aspirin bottle that had hopped a thread as she was trying to turn it, and it was stuck. And she was holding it like this and trying to turn it, couldn't get it to work. So what I did, I took it from her, held on here, and pushed at my elbow, instantly popped. Why? I had great lever arm. I had the length of my entire forearm to apply a force to turn it, rather than just the length of my hand bones. Okay, getting back to the teeter-totter or seesaw or whatever that. We have 2 torques on the system. The force for the child's torque is mg. So that would be 50 kilograms times 9.8 meters per second squared. And we're going to say that they're a length r away from the fulcrum. Now, going back to this, that means that this distance here is r. Well, then what does that make this distance? Well, it would just be the length of the board L without however much of it was r. So our lever arm for the kid is r. Our lever arm for the adult is what's left over if you take r away from the length of the board. And if we want these two torques to balance out, that is, the torque to make it rotate this way to be equal to the torque that makes it rotate this way, then we are asking for the two torques to be equal to each other. Or you could think of it as this torque plus the opposite directed torque would be 0. And in this case, one of these would need to be negative. Usually clockwise is the negative one. I'm just going to set them equal to each other so that I don't have to deal with any negative numbers. 200 kilograms, 9.8 meters per second squared, L minus R. 9.8 meters per second squared is on both sides. It cancels. And we're going to rewrite it with less stuff. You're going to need to distribute 50 kilograms R equals 200 kilograms L minus 200 kilograms R. We can move stuff to combine like terms. That's the phrase. That would make this 250 kilograms R when we combined the 200 with the 50 equals 200 kilograms L. We want to know the R, how long the lever arm is for the kid, because we're still assuming that the kid is at the 0 point. So if the kid is 0, then the fulcrum is located R away from them. So let's solve for R. We're going to get 200 kilograms L divided by 250 kilograms, and we get 4/5 the length of the board yet again. So, like I said, it works with either method. Let's try another one. Instead of trying to find the center of mass with this one, let's use torque for torque's sake. We know where the fulcrum is. The fulcrum is 1.5 meters away from the beginning of the board. Alice is about to dive into the water. She is 6 meters away from the beginning of the board. 3 meters away from the board beginning is the weight of the board, that is the center of gravity of the board is producing its weight from that spot. Thus, this must be a uniform board. Why? Because the center of mass is in the center of the board. And at point A, the beginning of the board, there are bolts holding it down. Point A is bolted down. What force must the bolts hold the board down with to prevent the board from rotating and sending Alice falling into the water? And then it flips over and conks her on the head. She passes out, blood all up in the pool. Terrible. Thankfully, it's bolted down. So we have two torques on this side of the fulcrum. If we want no rotation, then the sum of torques needs to be 0 Newton meters. Newton meters, of course, being the force times the length of any separation. Like I said earlier, torque can also be measured in pound-feet, although for some reason it's typically said backwards as foot-pounds. whatever. So Newton meters of torque. We want the sum of them to be 0, which means that these that go in this direction have to be equal to the 1 going in this direction, because it is implied that there is a force F here from the bolts pulling downward. So we need our torque in this direction to be equal to our torque, the sum of torques actually, in the opposite direction. So we filled that in, remembering that torque is force times lever arm, and it only counts if it's at a perpendicular application. Now, if this thing is not rotating and it's horizontal, then absolutely we have all 90-degree angles. So every one of these forces is entirely applied, creating torque. There's nothing going to waste. This torque here would be provided by the force of the bolts, which is 1.5 meters away from the fulcrum. If you were to try to do it like this and you add all the torques and set it equal to 0, then you would have to either have these be negative because they're going clockwise, or this side would be negative because you want it to be negative and you're ignoring the convention. You don't have to worry about the negative thing if you just start out with it already moved to the other side. Of course, sine 90 is 1. Do you want me to write that? No, I'm not going to. The torque from the board's weight is 850 newtons of force from the weight applied how far from the fulcrum? Well, from the bolts to the center of gravity of the board is 3 meters. 1.5 meters of that is in front of the fulcrum. So from the fulcrum to here must be 1.5 meters. Alice's weight is 650 newtons. And she is at the 6 meter mark from the beginning of the board. Again, we need to take out 1.5 meters. So she is 4.5 meters away from the fulcrum. 850 times 1.5 meters, we have 1,275 Newton meters of torque from the board, along with Alice's torque, which is 2,925 Newton meters of torque. Now notice Alice provides a heck of a lot more torque, not because she's applying more force, but because she has a greater lever arm. Combine your like terms, and the net torque going in the clockwise direction is 4,200 Newton meters for the force from the board's bolts. Be given as such. Meters is on the top and the bottom, so it cancels. Divide 4,200 by 1.5 meters. And these bolts have to be holding down with 2,800 or 2,800 newtons of force. Seems like anyone with a GPA greater than 2 in high school with even a passing interest in science thinks that they're going to grow up to be a doctor. So perhaps we should do some biophysics. That way when you get to the MCAT, you can say that I did not leave you unprepared. We have arms, or at least some of us do. In the human arm, you have a joint where 2 bones meet, the elbow, and then in front of that, just a little bit, is the bicep. The biceps can pull your arm toward you. Now notice this is a rotation type motion, so they must be providing a torque. They provide a torque by exerting a force upward some small separation away from the elbow. It's about 4 centimeters away from the elbow joint. Now, I don't know by what unspeakable process someone figured out the arm has a mass of about 2.5 kilograms, but here we are. The center of gravity, center of mass of the arm is where we can say all of that mass is exerted from one point. And then over here, we have the center of mass of a book being held up in the palm of the hand. So in order to keep that arm nice and level, how much force must the biceps exert? It's going to be a lot easier if you take it and turn it into a simpler notation problem. Instead of drawing out all the bones in the arm, just draw it as a little beam. The elbow is our fulcrum. There is an upward force from the biceps, force of the biceps, 4 centimeters away. 16 centimeters away from the fulcrum. Now notice that this is on the same side of the fulcrum as the bicep. So it's not like the last one with Allison's diving board where we had to subtract lengths of the board from the location of the fulcrum. We're measuring from the fulcrum, which is all the way off to one side for all of these. It's a little bit easier. And the force exerted is just the weight of the arm. That is going to be the mass of the arm times gravity. And finally, 38 centimeters away, we have the mass of the book pressing down on the arm from the palm. All right. So we have 2 torques going clockwise and one that is going counterclockwise, and they should be equal. So this is going to be equal to our 2 torques in the other direction put together, the one from the arm and the one from the book. The other way to think of it is that our net torque is 0, and these are negative. So when you move them over to where that 0 is, they become positive. Whatever is easiest for you to follow. All right, so let's start turning these into torques. The force of the bicep is applied at 4 centimeters. Let's turn that into meters so that we can get an answer in newtons for our force. Mass of the arm is 2.5 kilograms. Gravity is 9.8 meters per second squared. And we have 16 centimeters of lever arm. Get it? Lever arm. 4 kilograms. Gravity pulls down on it, giving it 9.8 meters per second squared of acceleration. And it is 38 centimeters from the elbow. Solve some of this stuff out so that we can begin to combine like terms. 2.5 times 9.8 times 0.16. 3.92 Newton meters of torque from just the weight of the arm. From the weight of the book, we have 4 times 9.8 times 0.38. So we get 14.896 Newton meters of torque from the weight of the book. These 2 torques combine, and this balances out both of them. So since our lever arm can't be very large, our force is probably going to have to be huge, kind of like opening the fridge from near the hinges. Put these together, and it's 18.816 Newton meters. Force of biceps lever arm. Divide each side by the lever arm from the biceps. And we will have the force applied in order to balance this out and create that counter torque. The force of the biceps must be 470.4 newtons in an upward direction. With that, I think we've done enough for you to attack our second practice sheet of the new order of things. So get to work. Adios, kids.